ინტერესების სფერო არის ქვის ხანის ადამიანი და ევოლუცია. ძალიან საინტერესო ექსპერიმენტების ავტორები არიან, რომელზეც ისაუბრებენ. ერთი როგორც ექსპერიმენტული არქეოლოგიის, მათ აქვს მრავალი ექსპერიმენტები ჩატარებული, როგორც ხდება ადრეული ეპოქებიდან და უმაღლესი მაიმუნების მიერ, როგორც ხდება ქვის იარაღების დამზადება. დღეს აქვს ძალიან ფართო კვლევა, რომელიც დაკავშირებულია ქვის იარაღების დამზადებას, კავშირი ქვის ევოლუციასთან. ჩვენ დიდი ხანია თანამშრომლობთ, ბევრი ჩვენი კოლეგა იყო ინდიანაში, დიდი საერთო პროგრამა გვაქვს, რომელიც ალბათ ისაუბრებენ, სადაც უდუაი, ჩინეთი და ამისი არის ეფიქსები. Plenობაში გეტყვით, რომ ესენი არის ძალიან მაღალი რანგის მეცნიერები ერთის მხრივ, მაგრამ მეორეს მხრივ ვიტყვი ასევე ძალიან საინტერესო კვლევარები, რომლებიც არ იფარგლებიან ვიწრო თავისი დარგით, ცდილობენ სხვადასხვა ახალი მეთოდებით გააფართოვონ ის სფერო, რომელიც ყველას გაინტერესებს ადამიანის ევოლუცია. Please.
Well, let me start by saying once again what a pleasure it is to be here and what an honor it is to get an honorary diploma from your university. Kathy and I have been married for over 40 years, and as soon as we got married, we went off to Africa and started doing research. So the big question we were asking is, what was the adaptive role of technology in human evolution? Why did we go from an ape-like ancestor, say 5 million years ago, to these incredible creatures we are today that are literally surrounded by material culture? So this is what we're trying to identify. And going along with that, we're tenured professors at Indiana University, but independently of the university, we raised the money, designed, and built this institute to study the Paleolithic. And it's been a great haven for us and a great place. You can see at the bottom right, one of our international workshops and conferences that we hold there. We hold one every year or two. In fact, David Javanya of the National Museum here is at that workshop. There are 4 major stages of human evolution we can talk about, starting with the lower left in the blue. These, what we call pre-Australopithecines, probably upright walking hominids with very small brains. As far as we know, no material culture associated with them, no archaeology. The next group are the early Australopithecines like Lucy, and by about 2.5 million years ago, we're seeing the first evidence of stone tools, possibly as early as 3.3, if the dates from a site in Kenya hold. So it's probably during this small-brained Australopithecine time that they start making stone tools. The yellow that you see are the robust Australopithecines, now assigned to the genus Paranthropus. They may have been stone tool makers, but they go extinct by 1.2 million years ago in East and South Africa. And finally, our genus Homo, we can trace the genus Homo going back between 2 and 3 million years ago, but it's at about 2 million years ago you're starting to see brain expansion. Most of these early sites traditionally were found in East Africa, in the caves of South Africa, and in open-air sites in North Africa. And the site of Dmanisi, which was discovered, recognized about 25 years ago, for having these ancient deposits, adds to this story now, which is very interesting. Kathy and I have worked at a number of localities in Africa and elsewhere, in the Gonan, Ethiopia, Middle Awash, Ethiopia. We did our dissertation work at Kubifor at Lake Turkana, Olduvai Gorge, and Lake Natron. And we were the first foreigners invited to dig in China since the Peking Man excavations in the 1930s. We started there in 1990. And the earliest Stone Age doesn't look like much if you're really interested in sculpture or aesthetics. They're very simple pebbles with flakes knocked off of them. We have battered stones that were used as hammers. And if you're fortunate enough to have bone preservation, you can see cut marks on those bones from stone tools, from sharp-edged stone tools, and fracture pattern bones from hammerstone and anvil breakage to get at the marrow inside. So for the early Stone Age, these are the usual suspects. The two on the left, the genus Paranthropus from South and East Africa, and on the right, traditionally assigned to Homo habilis in the center, then Homo rudolfensis and Homo erectus. And Dmanisi, again, has yielded 5 almost complete skulls to show us how much variability you might expect in a population, which has really excited the prehistoric world. I mentioned before we had a $3.2 million grant from the John Templeton Foundation entitled What Drives Human Cognition? And we focused on the time period 2 to 1 million years ago. And these 3 sites, Olduvai Gorge in Tanzania, made famous by the decades that the Leakeys worked there, Dmanisi here in Georgia, and the Nihuan Basin of China. And many of you have probably visited Dmanisi, an absolutely incredible site. Early stone tools, many animal bones, and these remarkable collection of skulls. And they estimate they've only dug about 5 to 10% of the site. So there's much more to find. U.S. Ambassador to Georgia, John Kelly, hosted our group there when we visited a few years ago. These are members of our Templeton workshop. And as I mentioned, we built into the grant the synergy of people visiting other sites, talking about methods and theory. We had another workshop in China, visiting archaeological sites, and one in Tanzania as well. The Templeton grant also focused on science education. We trained teachers at workshops. We sent teachers and students to museums and archaeological sites in Georgia and in Tanzania. And we built, on the bottom right there, you see a monument that was just constructed about 2 months ago that we designed at the turnoff to Olduvai Gorge, showing on the left the robust Australopithecine and its contemporary species on the right, Homo habilis, probably our ancestor and the probable toolmaker at Olduvai Gorge. Both of those skulls, the originals, would be about 1.85 million years old. And David mentioned our stress on experimental archaeology and actualistic studies, learning to make and use stone tools, setting out sites like prehistoric sites to see how they are buried by geological forces, etc. We've made thousands of experiments in making these simple stone tools called the Oldowan after Olduvai Gorge, so-called pebble tool culture. And this slide in the upper left, you see a hammerstone. These are basalt lava from East Africa. And the so-called core tools on the top that were the center of attention for most archaeologists going into the 1980s. The flakes that were struck off at the bottom there were assigned to debris or debitage. But our experiments, as you will see, suggest that these so-called pieces of debitage may have been principal tools of our tool-making ancestors. And you get these enigmatic objects, these battered stones called spheroids, from the very early Stone Age onwards. And there's been a lot of discussion of what these things were used for. Were they club heads? Were they thrown as missiles, etc.? But nobody actually tried to make them. So Kathy and I did a long experimental program. And if you take an angular piece of quartz or quartzite on the far left there, and you shape it by flaking into a polyhedral core, and then use it as a hammerstone, in 4 hours it becomes a perfect sphere. And so it's not quite as romantic as some of the scenarios of what these things are for, but it makes perfect sense to us that these are well-curated hammerstones that are carried around for future use. And at Olduvai Gorge, on the left axis there, the percentage of quartz in Stone Age populations and percentage of spheroids. As the percentage of quartz goes up in an assemblage, you get more and more of these spheroids as well. There's an association related to the raw materials that they're using. We're very fortunate to have extant apes that make and use tools. Jane Goodall first discovering that in the Gombe Reserve of Tanzania. And we decided they don't flake stone in the wild. So we wanted to see if we could teach apes to make stone tools. This is one of our prize pupils, Kanzi. He's a bonobo or pygmy chimpanzee. He was 9 years old when we started this in 1990. He's still alive and going strong. And we were able to, by example and showing him in trial and error, get him to flake stone. This is the guy who's jammed with Paul McCartney that I was talking about as well. Creating sharp cutting edges to cut through a thick cord to get into a food reward. So there was a payoff for doing this. And so he's producing things we would recognize in the archaeological record as artifactual. The pebble tools are cores and the flakes that are struck off. And Kathy and I flaked those same raw materials from the earliest archaeological sites at Gona in Ethiopia, gave them to our apes, and we were able to do a 3-species comparison of skill levels. And so here shows the skill. At the top is our human sample. At the bottom is the bonobo sample, lower skill. And the Gona hominids 2.5 million years ago from Ethiopia are intermediate in skill, but closer to what we were doing than what the apes are doing. I think the apes are challenged biomechanically. They don't have the selection for efficient flaking of stone, since it's not part of their repertoire. And I think also cognitively, you have to look for certain types of angles of less than 90 degrees, and both the Gona hominids and modern humans are much better at doing that. And it appears that at Gona, later stages of flaking are represented, not entire stories, so that they're flaking cobbles probably near a river and carrying them to another site for future use. So planning is a part of the biological and behavioral repertoire of our earliest human ancestors. At about 1.75 to 1.8 million years ago, we get the emergence of larger forms with larger brains called Homo erectus. The Dmanisi hominids would be examples of these at about 1.8 million years ago. And at some places, you get a shift in these technologies to what is called the Acheulean, named after a site that was discovered in the 19th century in France. Often, starting from the left, you have these boulder cores knocking off big flakes and making hand axes and cleavers. It takes quite a lot of power and strength to do this. It's very dangerous as well, because you're knocking off big, sharp pieces of stone from these boulders. And in about 5 hours, I was able to make 100 of these large flake blanks, where I could produce them into hand axes, cleavers, and picks, as you see at the top there. And Kathy will be talking more about what we think the function of these things. Why did our ancestors start doing this type of thing? By around 600,000 years ago, we have a new form called Homo heidelbergensis. Larger brain, almost brains as large as ours, but still massive faces. And they're making these beautiful hand axes, often in flint in Western Europe. You take a piece of flint, and in a half hour of time, I was able to produce one of these very symmetrical tools. We had the honor of traveling to New Guinea to study some of the last traditional stone tool makers as well. They're making hafted adzes to use in their fields, but the early stages of knocking off the big flakes and roughing them out, you can see in the foreground, an artifact that looks very much like a hand axe. We do a lot of experiments in the life story of a stone tool. When you find a stone tool, it's been discarded by a human, but we want to know the entire story. So this is a study of resharpening. That you see, there's a flint nodule, the first hand axe I make there, and if you were butchering an animal with this, for example, you would keep resharpening it as the edge dulled. And you can see how it changes in size and shape through progressive stages of resharpening to a very pointed form finally. We worked with surgeons at the Mayo Clinic in Rochester, Minnesota. They implant wires in our forearms and hands to study what muscles are critical in stone tool making and use. We've worked with kinesiologists to study the biomechanics of flaking stone, and we've done this with the bonobo apes as well. We're very interested in the evolution of the brain, which is a big part of the Templeton grant. And we did the pioneering work in seeing what areas of the brain are active during stone tool making and decision making. We used positron emission tomography in the pilot studies, and later we used functional MRI. This is my brain on the left making a simple pebble tool, and my brain on the right making one of these really refined hand axes that you might find 500,000 years ago. There are major differences in the areas that light up and more symmetry in the hand axe making. And if you look at how many cognitive decisions does it take to make a simple pebble tool, you can see about 11 for an Oluan pebble tool, but for a Ladishulian hand axe, over 4 times as many decisions that you have to make to achieve this form. Okay, I'll turn it over to Kathy.
Well, all of these aspects of our study that Nick has been talking about are very important to us. How they made the tools, how they accessed raw material, how they carried raw material around on the landscape. All of that is vitally important to us understanding these early stone tool makers and the dawn of technology. But if you think about it, that's missing also some important questions. Why in the world did they do this? Why did this become important? Why did it become part of their behavior patterns? And why did it continue almost seamlessly for the last 2.5 million years? So what was the function of these tools in the day-to-day lives, and also thinking longer term, the overall adaptation, the adaptive pathways that these early hominins were taking in these ancient paleo environments, and with a lot of competitors on the landscape, including other bipeds, as Nick mentioned. There are these robust Australopithecines, small-brained. Our early stone tool-making ancestors seem also to be relatively small-brained, but robust Australopithecines went their pathway, and our ancestors went this pathway. So let's explore some of our explorations of these early stone tools. And we've done a lot of functional studies, and we've quantified these in great detail, using stone tools for possible food-getting activities by these early hominins, such as nut cracking, bone breaking, and not only knowing how they work, but looking for patterns that might be produced in the tools themselves, or, for instance, in bone breaking on the bones. So this has been a very lucrative area of research for us and many of our colleagues in the past few decades, actually. We've also done digging experiments. You can dig. We've dug in East Africa for water resources. You can dig for underground storage organs that seasonally become very important to get you through, especially seasonal scarcity and above ground foods. We've also done woodworking, chopping with a so-called chopping tool, scraping a branch of wood into a spear or a digging stick. So we've, and you can analyze the stone tools and see what sort of damage patterns or other patterns that might be indicative when we finally dig these up a couple million years later. What can we see on those tools that might indicate what they were used for? And then also we think a very major use of these stone tools was in animal processing. And this was very important for our ancestors as a manner of expanding dietary breadth and having a competitive edge on those other competitors, both carnivores and the other hominins on the landscape. This was actually a scenario developed by Jay Maternus, who's done a lot of illustrations for National Geographic, and we asked him, we needed this sort of scenario for a project, and he said, oh, matter of fact, I did one for a Tokyo museum based upon a scenario you and Nick developed in your book, Making Silent Stone Speak. So he had developed it around our scenario with all the elements of the group and digging in the background and vultures and the food processing going on and bone breaking. So I'm going to show a few photos here of use of stone tools in animal butchery. I should make the point that none of these animals were killed for experimental purposes. They died of natural causes, and we were just able to move in and test our tools on them. So just to let you know that. So, oops, skipped one there. This is probably on the upper left, it's showing a simple flake slitting the hide of a wildebeest that had died in East Africa. You can see it's marvelously efficient, and we are not well equipped to do this activity just by our biological repertoire, nor were our ancestors at this time equipped to do this sort of activity. But with a simple stroke, you can make a very sharp flake and access large quantities of meat resources very quickly. The middle photo is showing one of these hand axes Nick was mentioning that is excellent for heavy-duty butchery. For dismembering, it has a built-in handle. You have a long serrated edge on one side, and usually you have a long serrated edge on the other side. So it's very useful. You can put a lot of weight into your tool and really rapidly deploy your group onto an abandoned carcass, say from a lion kill or scavenging a natural death for our ancestors, and get access to good haunches of meat very quickly. And the next photo on the lower right is showing a simple flake again, but accessing the meat on the bone. And this often leaves diagnostic traces that, again, we look for, and I'll show you a slide of that in a little while. And marrow processing. Marrow is an extremely valuable source of nutrition, of fat and other nutrients. And many hunters and gatherers have greatly valued this resource. And from the bone breakage patterns that you can see evident in experiments like this, and also that you find at early sites, you can find that they were doing consistent marrow processing going back a couple of million years. And also processing of the brain getting into the skull. And one lingering question in prehistoric studies and paleoanthropology has been, well, what good would these simple stone tools be in what we call megafauna processing? These large elephants, hippos, rhinos that sometimes you find in the prehistoric record. You say, well, what good would a simple Oldowan artifact do? This is an example of one of these elephant carcasses from Olduvai Gorge. It's a Mary Leakey's black and white photo of it, but there's a lot of the bones of an elephant and a lot of stone tools scattered around. So again, I'm going to go quickly through this next slide, but we again had the opportunity with an elephant who had died and to deploy our stone tools. And there's me accessing, slitting the hide of the elephant in the upper left, and there's large-scale processing in the lower left, and Nick is resharpening a hand axe there on the lower right because it gets dulled in use, as he mentioned, and you can start again with this refashioned edge of the hand axe. And then we've used in the past many tools, one of them the scanning electron microscope. We often borrow technologies from other departments, and as you saw with the positron emission tomography from medical schools, we borrow whatever technology we can get that will give us more information about these prehistoric tools, prehistoric sites. The scanning electron microscope can show very, very well delineated features of cut marks made from stone tools, such as this right here. There tend to be V-shaped grooves and very diagnostic. When they're clear, they're clear. And again, tooth marks that are diagnostically different, and we can differentiate when they're very clear. And I'll just divert a little bit here to show you some of the larger scale thinking that we have been doing about these sites. This is going way beyond the experimental. We engaged on a big geological coring project just a few years ago at Olduvai Gorge, which is often called the cradle of humankind. So we took off our experimental archaeology hats and put on our geological coring hats, and we knew nothing about geological coring when we started this, but we had a very fast, rapid learning curve. And we decided, well, coring, what's the importance of coring? Coring can give you very, very fine resolution strata that build up over periods of time, and you can pull out environmental information from those layers that were laid, both about paleo environment and by adding to it what you know about the whole depositional environment, you can figure out paleo environment and paleoclimate. So we did this at Olduvai Gorge in conjunction with well, Stone Age Institute, Indiana University, University of Liverpool, and our partner in Tanzania, Ngorongoro Conservation Area Authority. So we're trying to find paleo environments, the paleo-environmental context for human evolution, and how environmental adaptation was affecting human evolution during some critical periods of the emergence of stone tools, the emergence of larger-brained ancestors in our genus Homo, and the development of this Homo genus over time. And this is Olduvai Gorge. At the upper left, you see a Y-shaped gash in the Serengeti Plain. That's the gorge. There had been a great lake basin there during the time period that the hominins were living there. And we were going in to try to find these lake deposits through our geological cores and pull out all this information. And we went in, and we started on the day we projected, and we had a tremendously successful coring project. You see on the right, well, on the left is the geological drill. This is a big industrial drill that had to be brought up from central Tanzania. And on the diamond core bit of the drill there, and you can see the plastic tube that you pull out with these very fine layered sediments. And here you see in the laboratory, when we're studying them, you see the finely laminated lake clays and sometimes volcanic ash eruptions that almost look like a barcode. They're so detailed. And putting it all together, I won't belabor this, but we came up with three major cores. That middle section is representing our cores. One of them went 245 meters deep. We had, and we estimate that it's at least 2.4 million years ago. So we've been presently involved, about 38 researchers from 18 institutions in 5 different countries, and pulling out the detailed information about the environmental background here for this long sequence that we have at Olduvai Gorge. And we currently have a special issue of Paleo 3 that we're all contributing papers to. So it's, oh, and yes, and just to give you a sense of scale, your axis towers, those are scaled approximately to the extent of our cores. So you can see it's about 2/3 the height of our longest core, just to give a local impression of what we just passed those last night. So I grabbed it from the web this morning. And also we've extended the study of Olduvai beyond what we can drill down and pull up in a core. We developed a relationship with some seismologists from King Abdullah University in Saudi Arabia, and they came over, and it ended up that they found that rather than a shallow lake basin that people for decades have thought Olduvai Gorge was, it's really rather deep. And even our drilling has only gone down about halfway down. It's over 400 meters deep. And we think at the base of it, we're intersecting, we would be intersecting sediments from the sister Tanzanian site that's further to the south, Laitoli, where the footprints, famous footprints have been found. So, in fact, we are exploring developing a drilling project to extend down deeper to the bottom. So, and one more thought about thinking large. We have been really heavily investing in the infrastructure in our Tanzanian research. We have a new Olduvai field laboratory that has been completed. You can see it on the upper photos. Also, we've invested in solar panels. We fulfill the electrical needs of the entire camp now with our solar setup. And we've developed cisterns to develop water storage during the rainy season. So we're developing a really fine, more and more independent laboratory, independent of needing water brought in all the time. And we've also brought in microscopes and 3D scanners. This is a microscope that has, it costs more than the laboratory actually. And it has amazing ability to develop fine, detailed contours and surface patterns on bones and other materials. So we actually have this at the lab now. And on the left, I'm running a photo setup that we can take photos of artifacts or bones, and you can do 20 to 30 focal planes, and the photo system will stitch them all together into a wonderful three-dimensional image of the artifact. And it does it within a few minutes. So to sum up both Nick's part and my part about this story of the dawn of technology and the human prehistoric story surrounding technology, you have to really appreciate that humans, the human lineage, has undergone just an astounding transformation in the past 2 to 2.5 million years. It's hard to overemphasize this, how we have changed ourselves and our world and the rest of the earth. We've gone from a relatively small-brained and small-bodied bipedal creature, you may say rather insignificant-looking bipedal creature, going back 2 to 2.5 years ago, and developed over the course of the past couple million years a brain that's 3 to 4 times the size of the earliest tool makers, and developed this hugely technological world that we all live in. And we believe that technology played a major role, not the only role, but a major role in this transformation, that we were early on augmenting our biological abilities. We don't have sharp carnassial cutting teeth like dogs and cats do, but we can make a sharp tool in the blink of an eye. And we were augmenting our biological abilities with our tools in various dimensions. This really helped us expand our diet breadth and overall enhanced our ability to adapt to multiple environments, and very likely then helped enable the spread out of the African realm that we early on developed into others, including especially Demanissi, spreading to new environments and often new climates until now we've spread all over the earth and occasional forays off the earth, of course, which is, again, astounding. And this has produced many, many demands on cognitive evolution, on our capacity and propensity for planning, for problem solving. Even the earliest stone tool makers, I see them as early problem solvers, and early geologists, in a sense, for any geologists out there. They got to know their stones, and they knew which were going to be most efficient for many of their activities. And this also evolved into long-term learning. As our brain grew and we became, birth became earlier in the development of the brain, we developed very, very infantilized babies. They couldn't really support themselves without a lot of care, and then set up for long-term child development over many years. So life, really early learning period has been greatly extended in our species over that of even the apes. And also involved in this, what very likely we believe was enhanced group cooperation, and involved with this enhanced ability for communication and eventually human language. So again, it's a remarkable story, but it's true. And I sometimes say now that truth is stranger than fiction. If you made up this story, it would be remarkable. But tracing with our colleagues, good colleagues like David Wickenitsa and others around the world, this is the story that's emerging out of the human past. Oops. So, thank you.
So thank you very much for a very exciting and interesting lecture and walking us through history. I believe that we'll have more opportunities to meet each other. We'll have students here and part of faculty. And as we always told you, we're extremely comprehensive on technology. So all of your lecture is taken and it's on air and it's a live stream. So we're talking with many more students, as you can imagine, from this particular tea house. So thank you again for coming, and it was really a very interesting and exciting, intellectually rich presentation, and I wish you many happy returns. Thank you for coming.